Hi, hello friends. Welcome to my YouTube channel. Now, I'm going to start a lecture series on power system analysis. In power system analysis, the foremost important topic is fault analysis. So, in the fault analysis, first we are going to discuss the per unit system. So, when any fault occurs in power system, what is the equipment to be used? That is relays and circuit breakers are used when any fault occurs for the protection of the power system. So here I am considering a generator or alternator and a transformer. Maybe it may be a 10 kV to 230 volts transformer, for example. Say, okay, the circuit breaker should this circuit breaker should withstand for a minimum time up to when the circuit breaker contacts are open. That means the relay is going to sense the fault and it is giving signal to the circuit breaker. So till that point, the circuit breaker has to withstand its withstand capability. Now here, under fault condition, the higher currents are flowing through the circuit breakers, and the circuit breaker must hold the fault current till the signal is received by protecting relay. So until that point it has to be conducting only. So the breaking current, that is the capacity of the circuit breaker, and MVA of the circuit breaker depends upon the fault current and MVA rating of the system. Okay, so for example here let's consider we are using one circuit breaker for 33 kV line. So it's a 33 kV line and we are using circuit breaker here. And can we use the same circuit breaker for 220 kV line? No, so we can't use. Why? Because the breaking current capability of the circuit breaker is different and breaking current capability of this current circuit breaker is different. So do we use same circuit breakers for 33 kV and 220 kV? So definitely no. If the circuit breakers are not properly designed, causes failure of circuit breakers. So once a circuit breaker is failed, then the equipment which are connected to the system is such as transformers, generators, and some other loads are going to be damaged here. Okay, so load or transformer here. Next, the summary is the fault analysis is very important for designing of protecting equipments such as circuit breakers and relays. Okay, we'll move to the next slide. So in this slide we are going to compare the absolute system and per unit system. So generally electrical quantities are measured in two types. First, electrical quantities are electrical quantity are measured in two types. First one is absolute system, second one is per unit system. So I am considering here a generator and a transformer and a load here. So transformer may be 415 volts to 230 volts, or it may be any rating here. Okay, so in absolute systems all the parameters or quantities are volts, amperes, ohms, and power in volt amperes. So these are the units of these quantities. But if you go to the per unit system, there is no quantities, there is no units. Okay, there is no units here. And in case of absolute system, the number of equations are required to the equal to the number of voltages. That means here, from here to here, there is a one voltage, and from here to here another voltage is there. So here we require two number of equations here. In that manner, if we are going for any large power systems, we require large number of voltage equations to solve this here. And here in case of per unit systems, so no number of equations required to be is equal to 1 only. So how it is we will see. And what is the reason for this is, in power system the transformer causes the calculations more difficult. Why? Because a transformer is a place where the voltage ratings are going to be changed at each and every transformer. So this is the main reason for the uh, calculations are more difficult. Next one, the transformation ratio is required for calculations of impedances in case of absolute system, and no need of transformation ratios in case of per unit systems. Okay, the solution has to be done by step-by-step procedure, step-by-step manner here. So the time required is more here. the solution is to be done simultaneously so that the time required will be less. And in case of per unit system, the more storage memory is required. In here, less storage is required. Then how we are going to convert this actual system into a per unit system here? So for that one, the synchronous machine can be modeled as a constant voltage source with a reactance X per unit here. So that is why I represent a generator with a generator X per unit. This is the equivalent of generator. And how we are going to model the transformer in per unit system? So a transformer is shown here. It's maybe star star or delta star, which can be modeled as a reactance, a series reactance here. And the transmission line also can be modeled as a series reactance of X per unit. And induction motor loads can also be modeled as a reactance here X per unit and R dash per unit. So this is the per unit system. And here the main summary that we are going to key point here is the transformer has different impedances in absolute system but the same in per unit system. So this makes the calculations are easier in case of per unit system. So we'll move to the next slide. So now we'll discuss what's a per unit system. So in per unit system, per unit quantity is defined as absolute value of quantity in any units, either it may be voltage or it may be current or it may be power or it may be some other, divided by so base or reference values of quantity in the same units. So if you're taking voltage here also voltage, current here, impedance here, same unit should be taken here. So here the key point here is the base values is always larger rating in the power system. Okay, so what are the electrical quantities that we have here is the voltage, current, impedance, power, reactive power, apparent power. So now in this case, so in out of 6 electrical quantities, I will take 2 quantities as a base quantities here. So I'm choosing this one as a 2 base quantities here. So these 2 are the base quantities. So from these base quantities, I will take SB is a base value is equal to VB into IB. So IB is equal to SB by VB is a one formula that we got. That means from these 2 quantities, we find this unknown quantities. So we can find this I, Z, P, Q. All quantities we can find from this 2 base quantities only. So ZB is equal to VB by IB. It's nothing but PB square by SB. So IB is nothing but SB by VB here. And same thing here, next point. So if Z or X are given in actual values means all are having units of ohms only. So Z per unit is equal to actual value by base value. So same unit should be considered. So this is in ohms and this is in ohms. So Z in ohms divided by Z base that you got here, we substitute this equation. Now in our large power systems, connected systems, the power rating is always in terms of MVAs and kilovolts and kiloamps. That's why I will modify this equation. I will write this equation in terms of larger ratings. So Z per unit is equal to Z in ohms divided by, so base values of power is MVA base here and KVB whole square base. So this is a very important formula here. Okay, next line. If the Z per unit as per new base value, suppose if the Z per unit value is given already to you, now we want to find the Z per unit new value based on new base values. So at that time we will use this formula here. So we will use this formula here. Z per unit old is equal to Z in ohms into MVA old divided by KVB old whole square. And similarly Z per unit new is equal to Z ohm into ohm, Z in ohms MVA base of new divided by KVA base new whole square. So by using B by A formula, we can just find this value. Z per unit new is equal to Z per unit old into MVA new divided by MVA old into KVB whole square. So in any PSUs or especially in IES and GATE exams point of view, they will ask the questions based on this formula only. So very important formula for PSUs. So here those equations, the conclusion is the above equations are valid or used for only calculations of R, X, Z. That means we can represent here, we can replace this R. Suppose I will write here X per unit new is equal to X per unit old into MVA base new divided by MVA base old into, so KV base old square divided by KV base new square. So like this, you can use the same formula for R also for finding the resistance per unit. In the next slide, we will see the per unit systems for other than resistance, reactance, impedance. That means, suppose in an alternator having the SB is a generator rating, that is MVA, and h is the inertia constant, and m is the moment of inertia. So I want h per unit. So h per unit is nothing but h actual divided by h base value. So here assuming that s base, so actual values, h base is nothing but SB we are assuming here. So from this assumption, h per unit is equal to h value, actual value divided by s base here. So by using this formula here, so h per unit nu divided by h per unit is equal to, here one thing you have to observe, the h per unit is inversely proportional to s base. So here old means here old. So h per unit new and SB new. So h per unit old, h by old. So from this we can also apply for moment of inertia. So this is for alternator ratings. So next we will see for lagging loads. So for lagging loads means generally we will have induction motor loads. So induction motor loads are nothing but lagging loads here. So they will not specify this R and JX values. So if not specified, but they will specify the ratings in terms of its MVA rating and its a power factor. At the time what we have to do, in the exams they will ask what is the Z per unit of this load. So we will use this formula here. So Z per unit old is equal to S base divided by, so this is the actual base value and this is the actual value given into cos theta plus j sin theta. So it's a complex conjugate, don't forget this point. So in the option, in along with the options, so they will give the answer without conjugate here. So check this one. Suppose if the RL loads are in parallel, so parallel load means R per unit is equal to S base divided by S into cos theta, X per unit is equal to S base into sin theta. So this is a formula that we are going to use. Suppose if the values are given in terms of if S V is equal to Vm sin omega t plus theta 1 per unit values, and I is equal to M sin omega t plus theta 2 in per unit values, then S is nothing but this Vm into Im by 2 into per unit, and P is equal to Vm into Im by 2 into cos theta 1 minus cos theta 2, and reactive power Q is equal to Vm into Im by 2 and sin theta 1 minus theta 2. So these are the important formulas which will be useful in order to solve this per unit problems. In the next slide we'll use transformer per unit values. So in this session we will see how the transformer represented in per unit system, and how we can see the Z1 per unit is equal to Z2 per unit in system. So now I will take a transformer, and before going to discuss in detail about the per unit system, we'll assumption here, that is the shunt branch parameters are eliminated. That means these are the shunt branch parameters available in the per system, in our system, so these are removed. This is the first assumption, and the total impedance of the transformer is considered on either side, that's the primary side or secondary side. So if you draw the equivalent circuit of the transformer here, so we have V1, I1, R1, JX1 as it is, and we are referring this R2, JX2 to the primary side. So it is converted into R2 dash and JX2 dash here, and transformer, this is secondary. If you write the total impedance referred to primary side is Z1 is equal to R1 plus R2 dash plus J into X1 plus X2 dash, is nothing but total impedance referred to primary side. Z2 is nothing but, suppose if I change this, if I move these parameters to the right side, so here R2 and JX2 will be there. When you are converting this R1, it will become R1 dash, X1 becomes X1 dash. So total impedance referred to secondary side is Z2 is equal to R2 plus R1 dash plus J into X2 plus X1 dash. So friends, remember here that the impedance referred to primary and impedance referred to secondary are not equal in absolute systems. Okay, and now we know that in let's K is the transformation ratio. So K is nothing but V2 by V1, this is nothing but I1 by I2. So this is the absolute system. So now what I will do is, so K is nothing but I will choose a base value, so V2 base and V1 base. So base values are the maximum values of the system. So it's nothing but I1 by I1B by I2B. So this is the transformation ratio that I have chosen. Next here, so Z1 per unit is equal to Z actual value in ohms divided by Z1 base value in ohms. So we know this concept here. So Z1 divided by V1 base by I1 base. So Z1 into I1B by V1B. So from this equation, what is I1B? I1B is nothing but K into I2B, and V1B is nothing but V1B is nothing but V2B by K. So by substituting these equations, we will get this as Z1 divided by K square into Z2B. So this is nothing but Z1 into K square is nothing but when you are referring the transformer impedance from secondary to primary means it is divided by K square, and from primary to secondary means it's multiplied with K square. So based on this relationship, basic relationship, I can reduce that. So Z2 divided by Z2 base. So it's nothing but actual value divided by base value is nothing but Z2 per unit. So in per unit system, the Z1 per unit is equal to Z2 per unit of transformer, but which is not same in case of our absolute systems. So thank you friends, thank you for watching my videos. If you like my videos, please subscribe and like and comment. Thank you. In the next session, we will discuss the per unit system problems which are asked in previous year exams. Thank you. Thank you friends. Have a nice day. Take care.